Okay, so like Bo was saying, this is the Introduction to Software Exploits class. We're not talking about web app security or anything like that. This is all kind of low-level security, buffer overflows, that kind of thing. And just so you're all aware, this is a very lab-driven course. You'll probably be spending over half your time in this course, probably more like 2/3, looking into a debugger. So hopefully you like things like that, because that's what you'll be doing for most of the class. And it's important because with material like this, I can stand up here all day and talk about it, and if I walk out of the room, you would all forget, unless you do it yourselves. So hopefully by spending that much time with labs, you guys will walk away and be able to reproduce what we did in the class on your own. Okay, so about me. I'm Corey Kallenberg. I'm based out of the Colorado Springs site. I did work in McLean for about a year, but I transferred to Colorado Springs a few years ago. I've been doing exploits since 9th grade, maybe, something like that. Basically, I learned how to do all this stuff by doing a lot of hacking contests and trying to write exploits for vulnerabilities and stuff like that. It's mainly something that I do for fun. I like looking for bugs and zero days and all that kind of thing. I mainly do work in rootkit detection, kernel development, and I do some work with developing exploit mitigation technologies. Yeah, and I'm really bad at PowerPoint. And most of the PowerPoint slides were created using print screen, MS Paint, copy and paste, but it's not too important because we're going to be working in console most of the time and in debugger, so we're not about big flashy graphics because everyone knows that console is more GUI than having a nice fancy GUI. So, since I'm not based out of Bedford, I do kind of want to go around and get to know some of you guys. So, the purpose of this course is to really go in depth on a few key simple topics. It's not a survey course. It's not a high-level course. We're going to be hitting a few key concepts and hitting them over and over again to really ingrain them into your memory. Hopefully, in the course, you'll be able to sort of understand the implications of bad programming, to identify bad programming, to write your own exploits for some basic vulnerabilities. Also, understand better exploit mitigation technology. You hear all these things about ASLR depth. You'll have a better feeling of why these things are effective sometimes, where they're not effective, why they were invented, sort of the history behind that. And yeah, depth, not breadth. I've already reiterated that. Just as a disclaimer to begin the class, though, people have heard about buffer overflows, and that's generally what we're talking about in the class. And some of your friends might have told you, oh, buffer overflows are extinct, or exploit mitigation technologies render buffer overflows not exploitable. Both of those are completely false. Buffer overflows, even your basic ones, are still present in a lot of software out there. For you IDA Pro guys, just download some software that your sponsor uses and do a cross-reference on sprintf. You'll find lots of interesting things. And also, exploit mitigation technology does not render everything not exploitable. It makes some bugs not exploitable, but a large percentage of them can still be exploited. It just requires more work and more trickery. And we'll actually work on bypassing depth, at least in this class. And then in my Exploits 2 course, I'll basically have us, in one of our labs, blow away every exploit mitigation technology that Windows XP has to offer, at least. And for that matter, on Windows 7. Okay, so this is our course outline. This is kind of what we're covering on day one. We're going to talk about basic stack overflows. You guys have probably all heard of that, but you'll actually be doing them, so you'll know in gory detail how those work and how to implement them. Talk about developing your own shellcode. We're all going to write our own shellcode to do something. That's kind of fun for the guys that like assembly and low-level programming. So that's all about is handcrafting your own assembly. There's a lot of Stack Overflow, so we'll spend more time on that. And we're also going to talk about heaps and heap overflows. And these days, heaps and heap overflows are becoming more and more important because a lot of the browser-type vulnerabilities you see is sort of related to heap corruption and use after free and stuff like that. And I'll talk a little bit more later on about use after free and these other exploitation scenarios involving the heap. But let's not concern ourselves with that right now. It's heap is a little bit crazy. So day number 2, day number 1 is mostly devoted to sort of understanding the mechanics of exploitation, learning how to write your own exploits. It's really kind of the, just once you've found the vulnerability, how do you exploit it. Day 2 spends more time on actually identifying these vulnerable scenarios. That way when you're looking at source code for your own project or for a sponsor, you can recognize, okay, this is maybe bad, I should check this out a little bit further. And we're also going to talk about exploit mitigation technology. And see, the pros and cons and weaknesses and strengths there. Okay, as I've already mentioned, this is a completely lab-driven course. You're going to be spending most of your time in GDB and at the console. So prepare yourselves for that. Hopefully you'll enjoy debugging because you'll be doing a lot of it. Probably 90% of exploit development involves just staring into a debugger. GDB if you're in Linux or WinDebug if you're in Windows. All right, so let's get started with the actual material now that I've gone through all the sort of prerequisite information. Also, if anyone has any questions, including you remote people, please ask me right away because I know this material is pretty complicated. In fact, it's really very complicated at times. And sometimes I sort of take for granted that I've been doing this for a long time and I forget that things that are sort of natural to me because I've done them 100 times seem really strange and crazy to you guys. Also, one thing that we're going to try to do in this course that I have not done before is I want everyone to try to keep a sheet of paper or something to keep notes on, even if it's just a notepad. And every command that we use, like in the debugger, I suggest that you write that command down, like in a notepad or just on a piece of paper, and maybe jot what it does. Because I've had all my students in previous courses, ask for basically a cheat sheet. But if I just give you the cheat sheet, I feel like you kind of won't remember it as well. So if you actually just make it yourself as we're going through the course, hopefully you'll remember these commands better and you'll be able to reuse them. They all do appear in the slides pretty well for you to look at, like, oh, how did Core do this or how did Core do that? But it'll just help you out if you have them all in one place. Because I know some of the commands are pretty esoteric and not very intuitive. Okay, so here you go. Here's your first exploit that we're going to see in this class. This was a real exploit back in 1999 or whenever it was this movie came out. I don't remember exactly. The Matrix, this was some SSH exploit, which obviously no longer works, but back then, before the days of the movies, this was some kind of buffer overflow in SSH, and that's what our protagonist here is using. So just kind of funny that they're actually using a real exploit there in the movie. Before we get started on trying to actually develop exploits, let's just keep in mind what our goal is. Oftentimes what we're doing is extremely complicated and we can sort of get lost in what we're trying to do. So always keep in mind, what is our end goal? And in this class, our end goal is arbitrary code execution. We want to toss an application to do our bidding, do whatever. So for instance, you have like an HTTP server, like Apache, and you want to allow it to give you arbitrary code execution. So instead of just serving up HTTP sessions, it instead gives you, a shell or something like that, or anything else that's useful to the attacker. Instead of just parsing HTML, it's now downloading a rootkit from some website and then installing it on the web server. So basically, it's turning a process from what it was intended to do and making it do whatever you want it to do. Okay. This is the first program. I'm here on slide number 11. Are you synced up? Did someone tell me that? Yeah. Okay. So slide number 11. You see on the left pane there, this simple login program. This is the first thing that we're going to be exploiting. And this will sort of teach you the basics of Stack Overflows. So the first approach we take is, okay, let's take the Hollywood approach and see how that works out for us. So obviously, this is what they do in the movies. They just sort of automatically have some crazy program that has a password or something like that. But here that doesn't work. What a surprise. So the way that we're actually going to exploit a program is going to look more like this. So this probably looks a little bit crazy to you guys now, but I promise you by the end of the day, you will know what every byte of this payload means, because you'll be constructing them yourselves all day. Okay. Before we can start exploiting, though, it is integral for software exploitation to have an in-depth knowledge of x86, our architecture, our target architecture. So out of curiosity, who in this class has taken Zeno's x86 classes? So let's just review some basic x86 stuff that you're going to absolutely need to know to write these exploits. Okay. So just like in ARM or something like this, in x86 you have a bunch of registers like EAX, EBX, ECX, blah, blah, blah. There's a bunch of them. You have to know all of them. Two registers, or actually three that we really care about, are EVP, ESP, and EIP. So who in here knows what ESP is? Yeah?
Stack pointer.
Stack pointer, right. So does the, okay, Harry, I'll give you next time for one of the questions. Now, do you know in x86, does the stack pointer point at the next free entry on the stack or the last used entry on the stack? Does anyone know that? Where does ESP point to in x86? Yeah?
The last used.
Last used. So when you do something like a push, there's a subtraction of the stack pointer first and then the entry. Okay, now who knows what the EBP register is? Yeah?
Frame pointer.
Frame pointer. And what is the purpose of that?
Mark the beginning of a
Stack frame. Yeah, and don't worry about all this. I'm going to draw this out on the board a little bit. Just want to see where you guys are at. And in EIP, who knows that? That's what we're after. Yeah? Pointer. Right. So when we can control EIP, you know, that means good for us. So whenever you see EIP equals 41414141, you should go, yay! But not really, because that's only half the battle. All right, so I'm going to sort of draw out what happens on the board with the stack when we step through a program's execution, because we have to know this just in gruesome detail to be able to develop exploits. And then after I've sort of done it abstractly on the board, we'll actually step through the debugger and see if it actually happened in real time, and hopefully that will teach you some of the basic debugger commands as well. Out of curiosity, who in here has used GDB before? Okay, a lot of you, great. And for the remote people, it's okay if you have not. In fact, usually most of my students have not worked much with GDB, but you'll be pretty good at it on either class at least. Do you guys use WinDebug at all, out of curiosity? Okay. WinDebug is actually pretty good. Okay, so Bill, I'm going to write some stuff on the board here, so if we could point at the board, that would be good. All right, so I can read that. So I'm just going to draw what happens to the stack and what happens to the registers during the execution of this program, this simple login program. So hopefully you guys can just look at the source code and sort of figure out what's going on. So, most importantly to remember is that this is kind of crazy, but in x86, and I'm not sure about ARM or whatever, but in x86 the stack grows down, okay? So whenever you need to add space to the stack, you're basically subtracting from the stack pointer. So, that's really hard to remember. Yeah, let me find the winner here. Almost. And Bill, please let me know if the remote students are having a hard time seeing what I'm drawing on the board.
Okay, I'm going to zoom in on anyways once you get down to some detail.
Yeah, I know. I'm just trying to decide, not to screw myself and give myself enough board room here. Okay, so ESP is moving down more and more space within the stack. So every time, or here's another question, what is stored on the stack? Anyone in, any remote users? Anyone in here? What's stored on the stack?
parameters.
Parameters for so arguments. Yeah. Local variables.
Local variables.
Yeah. Okay. Return addresses. That's what we're after. State frame pointers. So basically all this junk that we just listed off accumulates on the stack as our program is executing. Let me know if I just wrote it myself. So, so we have like local var 1, ESP comes down to give us more space. We just created another local var. Let's say over in our source code we're doing something like integer local v. So each time this happens, basically our stack pointer is moving down. And what happens is when a program executes, or when a function executes rather, let's say we have a function like f, and it's going to create 3 integers in a b. What you would see in the debugger is instead of subtracting from the ESP each time, it would just do a mass subtraction at the beginning to make room for all this stuff. So to make room for these local variables, how much space would be subtracted in x86? 12, right? Because integers are 32 bits in x86. So if you were to look at this function in a debugger, you would see something in the beginning like sub ESP 12. So just moving the stack pointer down to accommodate the room for all these local variables. So that's kind of what's happening with the stack. Now, another important register to talk about is the frame pointer, EBP. And basically, when you have a function executing, the processor sets up EBP to point at we'll say right here. And this is our frame pointer. And the frame pointer basically just gives us a reference point so we can locate all of our local variables. So let's say that 12 bytes was subtracted here because we have 3 times 4-byte integers, 4-byte values. And their space, I'll just say this is a stack, that's kind of like their 4-byte space on the stack. So we'll say it is 1, 1, 1, 1, 1. A is 2, 2, 2, 2. B is 3, 3, 3, 3. And EBP is pointing somewhere up here above them. And whenever the program wants to reference one of these local variables, what you actually see happening is, let's say it wants to move the value of integer n into a register like EAX. What you would actually see is something like move EAX EBP minus 4. So EBP is pointing here, minus 4 points to here. So basically it's just giving us this reference point that we can use to reference all of our local variables. That sort of makes sense to you guys? Okay. Now, what happens is that each function has its own set of local variables. So let's say inside the f function, it's creating some local variables, integer n, but then it's also calling some other function. And then g, this function here, is using its own local variables. And so we'll say g syntax is plus doing something and it's making another integer. So what I'm trying to demonstrate here is that each function needs its own reference point because each function has its own stack frame on the stack, right? So after g exits, if this function wants to mess with its local variables again, it has to make sure that this frame pointer, EBP, is still the same. And EBP has a different value for the f and n and the f and g functions because they each have their own sets of local variables, their own stack frames. You guys sort of remember all this from x86 and stuff, right? Is this all wildly confusing to any of you guys? This should mostly be a review. Remote guys, are you following us okay? Bill, you can just sort of give me a consensus.
We have a yes, and a sort of, and a sure.
Okay. All right.
And Zeno is telling you to full screen your slides.
Okay. How do I even do that?
F5. Or Shift F5, actually.
Oh no. Okay. So Luther seemed a little bit confused about EVP and ESP and all that, and I know that my description up here is a little bit vague, but what's going to happen is that we're going to step through this program in the debugger and look at the values of all those registers, and hopefully doing that will make it a little bit clearer what's going on. So we can sort of step through this. I've already kind of done on the board what the stack will look like with this program as it executes. So in the main function, the first thing that happens is the authorize function is called. So EIP is going to start pointing at this block of code. And a couple things are going to happen when you see a call like this. And in fact, let's go ahead and just fire her debugger, and so we can see this happening in real time. Okay. So everyone try to start up your virtual machine. Has everyone in Bedford done that already at least? Okay, yeah. So on your desktop you will see a TSP425 exploits directory. And if you have, actually I think Mike said he fixed it already. So if you just go into the Slack 12 directory and double click on this VMX file, you should have the VM come up, and it might ask you like, did you move this or copy it? Just put the default answer, I copied it. And if you up in the left corner, you should see like a play button to use the virtual machine. So I'll give everyone a minute to get that going. Everyone in Bedford got their VM up? Any problems?
Yeah, what's the login and password?
Login and password for the computer for the VM.
For the VMs.
It's student and student or root and root. You should probably just use a student user.
Okay.
Yeah. And if you want, Xlinux is actually installed in virtual machines. If you want to use it, you can just type start X, but you're probably better off working in console. The only reason I have Xlinux started up in mine is so I can make the font bigger more easily. Yeah, you guys will have to excuse me if some of this has to be like, just a little bit slower than usual. And that's because we're videotaping this class for open security training today, which is a website that Zeno and I run. Zeno really orchestrated it to post all of our security training. So we try to, filter out anything like that. So, virtual machines. Everyone running them? Good? Okay. Remote users, got the VM started. Okay, so the remote guys are getting stuff still figured out a little bit, so while we're waiting for them, I just want to show you the slides again and sort of show you what we should expect to see. So there we go, there's a stack, the program just started executing. Let's look at what happens when this authorize call is hit. So when authorize is called, a couple things happen to the stack. The first thing is that whenever you see like a call function in x86, the first thing that enters onto the stack is the return address. So whenever you see a call, it's really like push next EIP and then jump to the function address. So it's just pushing that return address onto the stack. So here we go. There's the return address, and who knows where that return address will be pointing to in main?
Next instruction.
Yeah, but can you tell me what the next instruction would actually be? It's just a bit of trivia. You don't actually have to know this. So it'd actually be pointing at some code to handle this conditional statement, right? In x86 would probably be something like test EAX to see what the return value was for this function. Not too important. The next thing is that gets pushed onto the stack. And this actually happens at the beginning of the execution of the authorize function. We'll see this happening. Is that the actual call function sets up the return address, but the authorize function code is pushing this old frame pointer, the main function's frame pointer, onto the stack as well. That way we can restore that when the authorize function is done executing, and main can continue to reference its local variables, even though it's not doing so. And the next thing that ends up on the stack is you'll see that like sub ESP 64 bytes, and that's to make room for authorize's 64-byte buffer there for 64 bytes of local variables. So whenever we see this function call, the new things that are getting added onto the stack are saved return address, saved frame pointer, local variables. Okay, we'll see that in the debugger.
Hey, Corey, there was a question from Debbie about is she supposed to be opening something specific? She has it running.
No, not at this point. Just as long as she can log in with the student and student credentials.
I just had a question.
Sure.
This stack that you're showing, doesn't that first entry to return address at the main is only after authorizes call?
The return address in the main actually happens as a result of the call function. So that really kind of happens in the main function. And if you look at main, which we will do, you'll see something like call authorize. And when that x86 call instruction happens, it's really pushing that return address onto the stack automatically. The other stuff is getting set up by the actual authorized function code. And this may be different on different architectures, but at x86 and like x64, this is how it works. Okay, so we've seen enough of all this abstractly. Let's see it in the real deal. So, hopefully at this point, we all have our virtual machines going. And what I want you to do is compile the simple login program, but I want you to use TCC, not GCC, because TCC is a TinyC compiler, and it doesn't do any crazy optimizations like GCC does, and that just makes the assembly code a little bit more predictable. Whereas if we compile something with like a standard compiler like GCC, it's going to try to optimize our code, and it's going to make our stack look a little bit unexpected. So to compile it, and everyone should be writing this kind of stuff down on a little sheet of paper, unless you're pretty comfortable with Linux. It's like GCC, except you should fill in this G flag, because if you don't, GDB will basically mark on the executable and what it is. So TCC TinyC compiler -G -O, simple login, whatever you want to call, call the output an executable, simple login.c. And so remote guys, try to keep this sheet of paper with commands that you're using, and that's one you're going to want to write down, is that TCC command. That way you can just have that at your disposal for later. You don't have to go flipping back to the slides. But like I said before, all these commands will be on the slides, so you can just kind of flip through and find them. So just remember TCC, not GCC for now, because if you use GCC, you'll get wildly lost when you're stuck in one find like one. Okay, now to before we even start debugging it, let's just run the program a couple times to get a feel for what the program is supposed to do and how it works. And that just gives you a better idea of when you're actually debugging the application, what you're actually seeing in the debugger. So if you just do / simple login to run it, it's going to ask you for a password. And you enter in the wrong password, it's going to tell you that it's not the right password. If you enter in the right password, it's going to spawn a shell for you and give you that nice classic message. So that's basically all the program does. And that will just help you identify what you're looking at in the debugger. Is everyone remotely able to get the program compiled? Is he going to scold me for no? We're trying to make this look good for the webcast. And this is the first time I've done this, so I'm trying to make lots of mistakes. So let's go ahead and fire it up in the debugger. GDB, simple login. And just to make sure everything's working good, you can type, this is another one I'm going to write down, disassist, which is short for disassemble. Main, which is the function you want to disassemble, just that main function. And if you enter, you'll sort of see the code, and hopefully, since all of you guys at least know ARM pretty well, knowing what the C source code does and looking at its assembly should sort of make sense.
Corey, what was it? Can I just do
Disassist, so, there might be some shorter mnemonics to some of these commands. If any of you GDB guys know them, feel free to tell me. And so looking at this and knowing what the C source code does, it shouldn't be too surprising, right? So we call the authorize function. You're just going to ask for some input. The test function is checking the return value. If it's one thing, spawn the shell together, print, you're wrong, something like that. So what we're going to do is actually step through this function and see what happens to the stack. So here's another command for you guys to write down, you non-GDB guys. Break asterisk main plus 9. What we want to do is break on that call to the authorize function, just so we can sort of see what's getting put onto the stack and see the stack in real time. And the asterisk is important, otherwise it won't work. Oops, don't type disassist in front of that. So just like that. There's another one for you guys to be keeping for your notes.
Does GDB have a way, sorry, I'm no criteria, nothing about it, to explicitly tell it authorize instead of, because it seems to know the names of the
Yes, yeah, you can tell it authorize, but I want you to actually break before authorize. Okay, so break asterisk main plus 9, and then, I've got to get my Windy bug, GDB confused here, type R to go ahead and start the program, and then the program will run and we'll hit that breakpoint. And it's just since we compiled the debugging symbols telling us where we are in the program, but we know that we're basically right before that call function is about to get executed. So if at this point you were to do X, just look at the stack sum with this command. Here's another one for you guys to write down. X/10x $ESP. This is telling us X for examine. The slash parameter examine 10. U is hexadecimal. That's what the X is for. So examine 10 is hexadecimal. $ESP starting with ESP register. And this just gives us an idea of sort of what's on our stack before that call function gets executed.
So that's examining the contents of ESP.
It's examining the contents of where ESP is pointing at. So at this point, ESP is equal to OXBF, FF, F5, A8, and then at that location in memory is these values. Yeah, so instances like that where I sort of have forgotten that that's not that intuitive, please ask questions like that. So on the left, before the call, is kind of the address of the memory you're looking at, and on the right is the contents of the memory. Okay? So these are just things that are on the stack. Another thing to take note of is what these stack addresses look like. One thing that's very useful in exploit development is to have a feel for what addresses are just on how they look. So for instance, whenever you see like OXBF FF608, you know that that's like a stack address because that's just that range of memory. And what is that OX8080, 08048034 address? You don't know what that is? So that's just a code address. So that's somewhere, in our text segment. in our code. And you'll sort of pick up what all these are, is like B7, E9, or B7FE. Those are like the Linux-exploited modules like libc. Those are like libc addresses. And you'll just get a feel for what these are as we go through the course, but it's kind of helpful to know when you're looking at the stack, trying to debug something. Oh, that address is that, or whatever. Or that's a bogus address. Like if you see OX deadbeef, you know that's obviously bogus.
There's 3 entries, the A8, the B8, and the C8.
Mm-hmm.
Are those just those are all part of the ESP? Or are they the next?
Yeah, those are just looking at 10, let's see, 10, so is that, so yeah, 10 32-bit values. So those are 10 32-bit values starting at the address where ESP points.
Okay.
So in this case, each line has 4. And so since the width is 4, there's 4, 4, and then 2. So the 3 just comes from, that's how many they can fit on the screen.
Okay, and that's the reason it's showing 10 is because of that command 10.
Yes.
Okay.
Examine 10 X for hexadecimal. You could do X/10S for try to do as strings, or X/10I to try to do as x86 instructions, which we'll use that, and then the register that we want to view from, or you could just type the memory address in there. So you'll be using that command a lot, so make sure you have that one written down. Okay, so at this point, with the breakpoint, the call function has not actually executed. What I want you to do is set a breakpoint for the beginning of the authorize function. Break * authorize + 0, and this is just going to break us right as authorize is called. We could just single step into it, but just to make things explicit, we're going to type out the symbol name. So we know that the authorize function is about to be called because we've broken the call authorize. And so when we run again, hit R to run, or C to continue, sorry. It will have hit basically the next instruction is like basically a single step into that function. And we can see what happened to the stack. So this looks a lot like what we just previously saw, but there should be one new value. And if you'll notice, that first value looks a little bit different. It's a 0804836B, right? Just from your memory. That first address that you saw when you previously executed that command was OXBFFFF608. And to sort of sanity check these addresses, we can inspect each address individually. So what is that first address that we see? 0804836B. What is that address? What is it supposed to be?
Where it returns.
Yeah, the return address, right? Well, let's just push onto the stacks was the return address because we just executed the call function. And if we want to verify that, we can do X/, I'm just picking arbitrary numbers. And we can see that does in fact point back into main, and it points at the beginning of that code that handles the int_else. So no surprise there. Just sort of sanity checking the data that we're seeing. Is everyone with me so far? Just kind of understanding what we're doing.
Can I ask a question? I think I missed that last command that you had. It was the break * authorize +0? Okay. I just want to be sure I had it right.
Yeah. Yep, and then if you just hit C again, after you set the breakpoint, it should execute until you get to that breakpoint. Okay, so let's type disassist authorize and just see what the next group of instructions are about to be executed. So at this point, the call function has been executed, but none of authorize's instructions have been executed, right? Because of where we are in the process of execution. And you should see basically what I explained to you on the board. The first things that happen is you have push the frame pointer. That way we can save main's frame pointer. That way main can continue to reference its local variables once we return from this function. If everyone used the same frame pointer, they would all just collaborate with its local variables, so it's important that each one is unique. Move EBP, ESP is basically just starting our stack frame below the previous stack frame, that way giving us all new fresh space on the stack. Sub ESP OX40. Who knows what OX40 is in decimal? Yeah, right. Because our buffer, our local variables is basically a 64 byte buffer, right? That's where the sub ESP40 is coming from. And then that's basically those first three instructions. You're always going to see those because that's what's setting up the local stack frame. And then the rest of the instructions starting at authorize +9 is just the actual instructions to execute the functions code. Okay. So what I want you guys to do now is we're going to set a breakpoint for right after that stack frame is set up. That way we can look at a stack again and just see what's on there. So actually set the breakpoint for authorize +3. Because I don't want that subtraction to happen yet, because it'll put us far away from other stuff on the stack. So do break asterisk authorize +3. And then C. And then you can do like x/10x ESP again, so check out that stack again. And what's this latest value on the stack? Any of our remote users have an answer to that one? OXBF FF F5A8. What is that value? All right, note takers, it looks like. Anyone in here?
Our new stack frame pointer.
That's the saved stack frame pointer. The new stack frame pointer is actually in the register, right? The actual contents of the EBP register. What you see there is what the contents of the EBP register was during when the main function was executing. And we're just saving that so we can restore it. Here's another pretty handy command for you guys to know. I use this one a fair amount in exploit development. It's x/2x EBP. And before I even execute this command, who can tell me what this will display for us?
Just two values. It's just this.
What will those two values be? So if you execute
The previous stack frame.
and the saved return address. So when you're developing your exploits and you want to see what you've done to the return address at this point, use this command, x/2x or examine2, this hexadecimal, EBP. That'll tell you what is the saved frame pointer and what is the return address. That way you can see if you're corrupting those values or messing them up in some way, or if they're not what you expect them to be. So that's a good one to write down and have memorized.
But generally speaking, those should always be the same while you're in a particular function when everything's going the way it's supposed to be.
Yes, generally speaking. Sometimes you'll see crazy things happen. Sometimes programs actually modify their own frame pointer or save frame pointer or return address to do crazy things. But generally speaking, you should not see
Quick
that
question.
Sure.
So on that x2x command, is this essentially what you're saying is you're starting at the EBP and reading up
Yes.
two 32-bit words up the stack?
Precisely.
Okay.
Precisely. And stored and where EBP is pointing is a saved frame pointer. And then right after the saved frame pointer is a saved return address. And that's why you see that.
And that's above on. That's going up the memory address.
Going up.
Okay.
Going up, exactly. The X command will go up in memory. So if you do X10, it will look at the 10 address, and the 20 address, and the 30 address. If you told it to examine like 40 bytes or something like that.
And that's the opposite direction of what the
Stack is doing, yeah. Pretty good. Yeah, that's a little bit tricky. So,
So it'll examine.
so it's looking at increasingly higher memory addresses when you use the X command. Okay.
Okay,
But remember that the stack is going down.
of course, right.
So if you use the X command, halfway up your stack or halfway down your stack, you're going to be missing half of it. You'll be looking at all this stuff,
Yes.
and some of your stuff is down here.
Got it. Yep.
So that's something to keep in mind. And when we get to the heap, things in the heap grow upwards. So that'll be another fun twist to put on things. Okay, so at this point, we've stopped at authorize plus 3, which means authorize plus 3 has not executed, so we haven't created space for that local variable. And that's just creating space for that 64-byte buffer we have in the authorize function. Not too interesting. I just wanted to show you guys how that actually is used. So what I'm going to have you guys do is set a breakpoint for after the call to gets, which is reading our user input, our password attempt, and then we can look at the stack again and see what's on there. So I want you guys to set a breakpoint for authorize plus 32. And the way I'm getting it, authorize plus 32, that's correct, after the gets call. Okay? And so break asterisk authorize plus 32. C for continue. And enter in your password attempt, password or something like that. Hit enter. And now I want you to look at the stack again. Okay, so remember that command? It says we're on x/10 x. Oops. Does everyone see some crazy values in there? OX73, 736170, something like that, or it might be different depending on what your password attempt was. And that is basically just, the ASCII codes for the characters you entered in. All right. The first address you see there, which is a little bit crazy, is actually just a remnants of the call to gets, which hasn't been cleaned up off the stack yet. So if you were to do authorize plus 35, and basically I'm just bumping a task that, you see that add ESP4? That's just cleaning up some stuff, the arguments that were passed to the gets call. And see again, that way our stack is should be a little bit more sanitized at this point. And it's a little bit hard to interpret this if you haven't, looked at a lot of hexadecimal before. Like I can instantly recognize, okay, it's like an ASCII string, like a capital, like a PAS or something like that. But you can use the x/s command, which is another handy one, where I try to interpret this memory address as a string. And we can see that, hey, look, after the call to gets, this password string is on the stack. That's just because that password buffer was on the stack, and the password buffer has already been filled up by our password attempt. Okay. At this point, I want you guys to do this command. x/50 x ESP. So at this point, Bill, I'm going to draw something on the board again. Now this is for my stack. It might look a little bit different depending on what you enter in as your password.
Is it supposed to be a dollar sign or
Dollar signs. Or that should be a dollar sign. Okay. So this is my stack. All right. This is my stack in the program's execution at this point. The ESP register is pointing right here. This is the bottom of my stack. This is the outer limits. Go no further. This point. Right here is the P character. A, S, S, W, whatever. T. Anyone know what this character would be? Null terminal. Okay. Zero, zero. Because ASCII strings are always null terminated. Or usually only do different hashes in there, always. What's the next one? What would the next value on the stack be? Saved EDP. Where there's more space in here because we have 64 bytes of space, so blah, 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 blah. Later on, a little bit better. Blah, 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 blah. And then right at this point, we'll say is ESP plus 64. And then saved EDP, and then return address. So this is what my stack looks like. ESP plus 0, ESP plus 1, plus D plus 3, blah, 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 plus 64. And then plus 68.
But the dump from the x/50x would start from the bottom.
Yes. So what I want you to do at this point is change the command a little bit on you guys. And I'm putting the B in, which is look at byte values instead of 32-bit values, so 8-bit values, just so this kind of matches up with what I'm showing you on the board a little bit better. So x/70, examine 70 bytes and view them in hexadecimal, starting at the stack pointer. Okay, so we can see we have like EASS, P is OX70, 61 is A, 73, 73, 77, etc. And an old terminator. What's a little bit interesting and unexpected is that these values aren't null. You see just a lot of other junk values here after our string. That's because the stack is just kind of lazily deleted, so we're actually deleted. Old contents from the stack are still on there. We'll talk about how that can be a problem later on. And then later on down the line, you'll see like the, just let's identify them, let's see what they actually are. /2x, see what my return address and my save frame pointer are. Oops. So yeah, we can see the beginnings of those like right here. This is the state frame pointer. And if I gone a little bit further, that's the beginnings of the return address. Yeah, right, because the information.
So the B and W change the mode?
Yes. W is just switching back to 32-bit mode. Okay, so at this point, remote users 2, does everyone have a general understanding of what is on the stack at this point in the program's execution, where those values came from, and feel generally okay with where we're at in the material at this point? Is any of this wildly confusing to people? Good, remote guys, doing okay? So if you have any specific questions or would like me to go over any of those topics, please let me know. Okay, lots of sort of. I know the material is a little bit
I have a
confusing.
quick question.
Sure.
Every one of those, like when you drew password going up the stack, every one of those characters is represented by 8 bits, right? So
Correct.
is the stack not done by 32-bit words?
It is, but you can just interpret it as single byte values as well.
Okay.
It's all a matter of how you interpret it. But yeah, I mean, generally you're pushing 4-byte things on or off the stack.
So is it storing the P and then 3 blank bytes, or?
No, like you can see if you do, I mean, it's, if you look at them as 32-bit values, it appears as this, 73736170. And the 70 is actually the P, the 61 is the A, and the 73 and the 73 are S's. That's just backwards because little endian or big endian. I'll talk about that in a second. But you know, it's just memory, and you can interpret it at any granularity that you want to. So in terms of ASCII strings, the compiler just knows to interpret it at the 8-bit granularity because it knows it's dealing with 8-bit values.
So when you do it in 32-bit words, it'll put it in little endian word, but if you do byte at a time, it'll...
Yes, exactly. Yeah, and it's only putting in little endian mode because it's saying I'm on x86. So since he's asking for a 32-bit value, I'm going to automatically switch it to order since that's the way it normally works. Talk more about that in a second. So don't worry if you don't get that little endian or big endian stuff. But just remember, this is all just, you know, memory, like a big vector, and you can put whatever you want through there, and then how you interpret it, either as 32-bit values or 8-bit values, is completely up to you and the compiler.
You can also put it into character mode to make it a little more user-friendly.
Yeah, that's 10C, right?
Yeah.
Yeah, it just, it helps to be able to recognize that everything looks like it's hexadecimal when you're developing exploits, which is why I'm kind of having you guys do that.